Thank you. Hi, everybody. Happy Hump Day. Happy Hump Day. We're getting over the hill. Hello, Nookus. Hello, Hump Day. Squared circle. Hey, it's Wednesday already. Yes, it is. Bring me that weekend. Hello, Amin. And guys, it's a beautiful day out there. It really is a beautiful day. What is it? It's like 40 degrees. 48 degrees, says my phone. Mostly sunny. Hello, Amin. Hello, Chinghan. Wow. Might go for a nice walk later. That sounds like a plan. So I have a story for you. I was going to go on a nice walk this morning, and as I was walking out my front door, I almost slipped because we have like 2 inches of ice basically on this walkway, like just thick, laid on, slippery as can be. And so I decided that I had to take care of this ice. And we don't really have like a serious snow shovel. We have like a cheap plastic one that you're probably gonna break. And so I was like, how do I crack this ice? I went downstairs and just got like a hammer, just like your standard thing to hammer a nail. And then I spent like 45 minutes on our walkway just whacking the ground with a hammer until I broke the ice. And I scooted all the ice chunks away. I did the mailman a solid. Yeah, I was outside, bent over, hitting the ground with a hammer. Imagine being the neighbor. Yeah, they're like, what are you doing? Maybe not the most efficient way to do it. That's what I did. Mike says, I just got back from a run on this warm day. Maybe I'll do that later too. A run sounds nice. Where's your not a flamethrower? I would love to get my hands on one of those. Should have used a rubber hammer? Wait, that would how would that help? How would that help? Just got your fun car up and running? Done with the winter weather, time to bring out the fun car? Less damage to your driveway and hammer? Probably. All right, let's get started here. We have a fantastic code that we're finishing up, and let's review where we are right now. So when you design a control system, it's typical to have some constraints that look like this. You might have, I'm just going to make something up, settling time less than 2 seconds, rise time less than maybe half a second, and maybe an overshoot, let's say it's like less than 20%. And by the way, maybe your hardware has a sampling time of 10 hertz. So this is a way of using specific language to get our system to perform in a way that we can visualize nicely. And so we've been building a code to show us what discrete systems satisfy these constraints separately. So let's just quickly review some of these one by one. So maybe we'll just say this first. Stability is like a given for a control system. And this implies that the magnitude of your discrete roots has to be less than 1. So for a discrete time system to be stable, all of your roots exist within a unit circle in the complex plane. You're never a greater distance than 1 from the origin. So the next thing we talked about was settling time, and this also creates a circle in the complex plane. So let's talk about that. So you might say the settling time needs to be less than some constant. Maybe it's 2 seconds, I don't know. And what we discovered is that this implies that the magnitude of your discrete root that satisfies this, it has to be less than the exponent minus 4 over whatever that settling time is, times your sampling period. So this will describe a circle of some radius. The faster the settling time, the tighter that circle is going to be. All right, and then this is the one that we're almost finished with. We talked about overshoot. And so you might see a constraint like this. Your overshoot has to be less than some nominal overshoot. And this first implies something about your damping ratio. Your damping ratio has to be greater than the square root of the natural log of that overshoot that they give you, squared. And then you divide that by the same thing, that overshoot squared plus pi squared. So this tells you, okay, you want an overshoot less than 10%. Well, your damping ratio has to be greater than something. All right, so then this implies the next thing. The distance of the root from the origin, that's what the magnitude is, it has to be less than, we have the exponential of whatever that damping ratio is, divided by the square root of 1 minus that damping ratio squared, and then we multiply that by the angle of where this root is in the complex plane, and that all goes in the exponential. Now this is kind of where we stopped. You can see that in this case, this is a little different than the settling time because the magnitude is going to change as you go around the complex plane, because this angle represents, we got our imaginary axis, our real axis, and let's say we have the positive conjugate of a complex conjugate pair here. So you can describe the location of this root, number one, by its distance from the origin, so that's the magnitude that we're talking about. So the magnitude has to be less than this, but you see that the magnitude changes with this angle, which is the angle that we make relative to the positive real axis. So as we change this angle, this magnitude's going to change, and it makes some interesting shapes. It actually makes a heart shape for some damping ratios, which is adorable, that the mathematics just works out that way. So let's talk about this angle, though. This angle is only going to go between 0 and pi And I want to unpack this a little bit more. I know we've talked about it a little bit. But let's talk about it some more. So, for an oscillatory discrete time system, so that just means a discrete time system with complex conjugate roots, like this one. It always comes in pairs, so there's going to be a mirrored one down here. The explicit solution is going to look something like this, the explicit homogeneous solution. You're going to have the magnitude of that root to the k, so however far away it is from the origin, and then you multiply it with this sinusoidal function. So you're going to have some constant, I'll call it C1, times the angle times your step k, and then another constant times the sine of your angle times k. Alright, so I'm showing you this to connect the angle of the root in the complex plane to the frequency of oscillation. So when you see this angle in this cosine function, what this is frequency in radians per step, k. Hank says hey. Hey, Hank. Okay, so let's just think about the frequency of a discrete time system for a second. Ooh, hello from Georgia. It's probably lovely down there right now. The highest frequency that a discrete time system can oscillate, so let's put like step k as the horizontal axis and x as a function of k. If you think about it, maybe let's put some steps here, like k is equal to 1, 2, 3. The fastest oscillation period that you can possibly get. How did we reach this equation? I'm sorry, I think I got lost in the middle. So this equation we derived maybe 2 weeks ago. So I'm kind of taking it for granted right now. If you want to see how this is derived, go back in our notes a little bit. Okay, cool. Let's say we start at time 0 at like 1 or something. The fastest oscillation frequency I can get would be 1 cycle every 2 samples, right? Are you going to post these notes? Yes. Because if you have to come back to the original spot, and you have to go somewhere else before you can return to that same spot. So just in discrete time, this would be the fastest possible frequency. So, and really I shouldn't like connect these with lines probably. And this happens, it only happens when roots are on the negative real axis. But, okay, so we're going to say the maximum frequency, which I'm going to express it as this angle, because those are the same, it would be 2 pi radians per 2 steps. I completed a cycle over 2 steps. I got back to the same place. You could cancel the 2's, and it's pi radians per step. So this is the physical reason why, if we go back up here, I say that, look, this angle, which is related to the frequency, it's got to be between 0 and pi, because physically we can't oscillate any faster. So in our code, when we're building the shape that this overshoot condition requires, we're going to bring this angle from 0 all the way over to pi, and like the magnitude's going to be like changing as we do it. So the magnitude, it changes as a function of angle, and by the time we get to pi, it makes a shape like this. And then the conjugate root, like this one down here, that's going to mirror it, we're just going to create a mirror image in MATLAB to complete the shape of the heart. Okay, so let's go back to MATLAB. Let's go to where we left off. And here's where we were building that overshoot shape. So we're defining an angle theta, which, think of this as that angle lambda d variable that I was using in the notes a second ago. But this is going to go from 0 to pi. And then this zeta, this damping ratio, this is the same as this formula right here. So I have some overshoot, then I calculate what this damping ratio is. So that's this same formula right here. It's got the square root of the logarithm squared, blah, 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 blah. And then next we calculate the magnitude based on that zeta. And that's this formula. So we went boom, boom, boom. And in the code, I'm calling this angle theta, and we're going from 0 to pi. So there we go. And then, as I'm traveling across this angle from 0 to pi, are you going to post the code? No, I'm not going to post this. You have to earn this. Are you redefining theta here, or did the original theta get removed? Great question. I redefined it. Like earlier on in the code, I named a variable theta, just went from 0 to 2 pi. And I was doing this just because we were drawing circles for the stability boundary. We were drawing circles for the settling time, and I didn't worry too much about the boundary of the angle. So now I'm going down here, being a little bit lazy because I'm not making a new variable name. That'd probably be better coding practice. But this one's just going from 0 to pi. So I renamed it. And now I have the real part of the root as I trace this contour. So I just take the magnitude multiplied by the cosine theta. So I have the real and imaginary. That's true. The video is posted. You can always come back to this. You just made it theta 2. Let's do that. I like what you're doing. I'll call it theta 2. I'm gonna do the same thing. And for now, I'm gonna delete, because we were playing around with making this shape last time, and we had some different ways of doing it. But I'm gonna show you a new way that we're gonna have to use once we get to the rise time, or it's one way. Okay, so we have the real, we have the imaginary. Let's just run this code and see what it gets right now. It gives me an error. Wait. Oh, okay. Okay. We got an error because we didn't change that to theta 2. Now we're going to run it again. Ooh. Okay, so we went from 0 to pi, and the magnitude was changing, so it's making this shape, and then we filled in that shape. And where's my transparency? I think I need this alpha back here. This alpha command makes the shapes kind of see-through. Let's run it again. Okay, so now it looks a little prettier. All right, now I want to show you a way to mirror this shape. This is not the only way. I know we have other solutions to do this, but this is a way that I like. And this gives you some insight into how the fill command works, because this. So let's go back here. So before I do this, let's talk about the fill command. So what we're doing is when I'm drawing this shape, I'm starting over here and I have like a discrete amount of points and I'm going around. And then when I use the fill command, it connects all of these and then it goes back to the beginning as well. So it connects these bottom two and then it fills it in. So my strategy for mirroring this is instead of having, I'm basically going to add more points. So I'm going to add more points to this sequence where it's going to come around this way. And so instead of jumping across over there, it's going to keep going this way. It's going to come back and close the shape, and then it's going to fill the whole thing in. So let's talk about how we do this in the code. Negate the imaginary component. Yes. So basically, like if you think about it, we're going to start at some real number over here, and like the real component, we're walking over this way. And then to go back along this way, I'm going to have to march back the real component in the other direction. And the imaginary component, we're going to have to flip the sign. Okay, so here we go. So I'm going to add some code here. Real, and so I'm going to call this the real part, and let's name it 2. And this is going to be including the original real part. So this is like the top half of the heart shape. And then we're going to add the bottom half of the heart shape. But remember, we're going to go along the real direction, but like kind of in the opposite way. So I'm going to show you a command. You can do this flip up down. So what I'm doing is I'm taking the real component one direction, and then I'm going back the other way. So this flip up down command, it takes this vector, which is a column vector, and it just flips it around. Actually, let's run this, because I can make that clear. Figure, oops. Let's plot real MP2. So you can see the real part, it starts from 1, goes over to the negative, and then right here is where we flipped it up, and then it's going back where it came. So this is where we attached that piece. So let's do the corresponding imaginary. So we're going to take our original stuff that we made the top half of this heart shape. And then we're going to have to do the same thing where we trace it along the opposite direction, but we're going to do the negative of what we had prior. And if you get confused by this code, because I've confused myself many times, the best way to think about this is just remember how the fill command works. It's going to take the points that you give it and it's going to connect them in order. And so I'm trying to just sequence all of our points in an order so that it goes around the outside of this circle. And if you ever want to make more complex shapes with the fill command, just come back to this idea, like how do I continuously arrange my points to be the boundary? All right, so now we're going to use this fill command. We're going to use like this extended sequence of X and Y points. Okay, let's run it. Oh, I have to add the 2. We have to plot the 2 version. Oh ho 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 ho! Beautiful. So the roots, so the green, once again, is the settling time. This heart shape is the overshoot condition. It's gorgeous. And we need to look at the overlapping region to see the roots that satisfy both. Flawless, gorgeous, stunning. I know. It's just unbelievable. It's just like everyone here. That's correct. All right. It's time to make this even better. We're going to talk about the rise time condition next. And this is going to make perhaps the most interesting shape. Debatable? Come on! Okay, here is our formula for the rise time. It's 1 over the damped natural frequency times pi minus the tangent inverse of the square root of 1 minus zeta squared divided by zeta. So, just so you remember, we're looking at like the step response of some second order system, and it's gradually settling at some steady state amplitude. The rise time is the time it takes to cross that steady state value for the first time. So when you look at this formula, this is the meaning. It's that duration of time. And so when we're designing a control system, we might say, hey, your rise time needs to be less than 2 seconds, 1 second. Okay, so we're gonna figure out what constraint this sets on our magnitude and our angle and whatever, and then we're gonna plot that shape. So to make this just a little easier to write out, this tangent inverse is some angle. Let's just call it beta. Okay, so that'll just save us some writing. So I'm gonna say the rise time is 1 over that damped natural frequency times pi minus beta. And we're saying, okay, this has to be less than, I don't know, half a second. So what I'm going to do here, I'm going to rewrite this damped natural frequency in terms of the natural frequency and damping ratio. That's just the definition of the damped natural frequency right there. All right, and I'm going to solve for the natural frequency here. So it's going to be the natural frequency needs to be greater than 1 over this rise time, square root of 1 minus damping ratio squared times pi minus beta. And beta, it's a function of the damping ratio as well. So here's why I solved for the natural frequency out of this. For an underdamped system, I already know acceptable values of the damping ratio. So what is it? The damping ratio can be between 0 and 1. So to satisfy this rise time condition, I already know there's going to be damping ratios between 0 and 1 that can make that happen. And so when we go to MATLAB, I'm going to define a vector of damping ratios over that range. And they'll be substituted in beta and down here, because those are a function of the damping ratio. And then, for every damping ratio in this vector, so let's say for the damping ratio of 0.2, the natural frequency is going to have to be greater than something for each damping ratio. And so we're going to construct a vector of acceptable damping ratios, acceptable natural frequencies for each damping ratio to satisfy like this rise time constraint. So this is going to then lead us to what's the acceptable magnitude of the root and what's the acceptable angle. So let's put a not subscript for this omega n, because we've been using that as the indicator for a variable that satisfies a condition. So, all right, then this is the definition of the magnitude of a discrete time root. This is just the standard definition. It's the damping ratio times the natural frequency times your sampling period. So once again, in my code, that damping ratio, it's going to be between 0 and 1. This natural frequency is going to be the acceptable natural frequency that satisfies this for every damping ratio. And then this will just be whatever sampling period we have for our system. All right. And then the angles that go along with this magnitude. So for every magnitude, there's an associated angle. Oh wait, take one step back. I put an equal sign here. That is not appropriate because we're dealing with inequalities. It turns out that this is going to be less than, because if the natural frequency has to be greater than something, it's going to make this value up top in the exponential more and more negative, right? So basically, this results in a constraint that our magnitude has to be less than something. All right. Okay, and first I'll put an equal sign for this one as well, for the angle, and then we'll change it to an inequality. So the definition of the angle of a root, of a discrete root, is the damped natural frequency times the sampling period. Prayers for Tiger. Yeah, I heard he was in a nasty car wreck. So, yeah, thoughts and prayers go out to that dude for sure. Okay, how's the damped natural frequency related to the natural frequency? Natural frequency 1 minus a squared. Okay, so now we've unlocked this natural frequency term. If we're going to talk about this constraint, let's use this special natural frequency that satisfies the rise time. So this number, it's going to keep it has to be greater than. So this also means that our angle is going to need to be greater than this. Let's go to MATLAB. Let's start building this. I I think gradually it'll make more sense, and it's going to make a really cool shape. All right, let's go here. Rise time. Okay. So first, let's define that range of damping ratios. So damping ratio is zeta, and I said we're gonna pick some values between 0 and 1. But actually, we don't want to go all the way to 1. I'm gonna go to 0.99. Maybe I'll talk about that later. But if you go to 1, you get some like singularities in here. So we're gonna go close to that. And maybe we'll do like 500 points in between there. So we'll have a pretty fine resolution. Okay. Now, let's see here. In that rise time formula, I defined a variable beta just to remove some of the work. So I'm going to do the same thing in the code. I'm going to call this inverse tangent beta, and I'm going to substitute in that vector that I had from going from 0 to almost 1. Okay, so beta is the inverse tangent of the square root of 1 minus zeta tr squared. And look, I have to do this dot caret symbol. Why do you transpose some of these vectors? All the transposition that I'm doing here is to make everything into a column vector. So sometimes when you're coding, you can run into situations where you have like some row vectors, some column vectors. Just to keep everything straight in my mind, I just make everything a column so I don't ever get confused. I just saw something from Jack. Does the flip up-down function flip the order of entries in a series? Yes, that's exactly what it does. Column vectors, heart. Yeah, I think column vectors they're usually just the way to go. Okay, so we need the square root of this. And then I have to divide by... Oh yeah, the caret symbols, this just indicates element-wise division. This is element-wise power. So I'm taking every element of this vector and I'm raising it to the second power. And then every element of this resulting vector, I'm dividing by every element in this. And because I defined zeta to be a column vector, all of the math I do here will also make a column vector. So beta is a column vector. Okay, now this omega n, I'll call it TR for rise time. This is the formula for what the natural frequency has to be to satisfy the rise time constraint, which we didn't even define what that is. Let's put one at the top, because that's where we're putting all of our constraints in this code. So I'll say TR naught. For now, let's just say like it's 1. So this is the maximum rise time. So we need to have a rise time less than this. So I have that variable TR naught. Okay, so I'm going to have pi minus beta divided by TR naught times the square root of 1 minus zeta TR squared. So I'm just taking that same formula for the natural frequency. I'm putting it into MATLAB speech. So now we have that natural frequency. And I think to get the angle, we're also going to need the damped natural frequency. So let's calculate that here. It's just the natural frequency times the square root of 1 minus the damping ratio squared. Does TR naught need to be TR with the dot multiply? No, And the reason is because this is a scalar. So anytime you multiply a scalar with a vector, you don't need the dot. TR naught is the maximum rise time. It's kind of the constraint. Your rise time can be no greater than TR naught. So we're finding a system that has a rise time less than TR naught. Okay, boom. Oh, what? Oh, yeah. I made it equal to 1. Okay. Okay, so we're gonna make magnitude. The magnitude of the roots using these damping ratios, natural frequency up above. So it's exponent minus the damping ratio times the natural frequency times the sampling period. So that's the magnitude. And then the angle is omega d TR times T. All right, and for now, I'm just going to plot a line. Okay, well first we need the real, so we have the magnitude and the angle. Let's get the XY positions of the root as we trace this magnitude along whatever this angle is. So the real part of the root that makes this rise time condition is the magnitude times cosine of the angle. And then the imaginary is going to be that magnitude, but just times the sine. Okay, now we're going to make P4, our fourth layer of the plot. And I'm not going to use the fill command yet, because I just want to show you. This right here is actually just going to make a line. Okay, imaginary. Let's just make it a black line. I'll thicken it up with that line width. Actually, I'll just leave it like that. Okay, I'm going to run this. And this, my friends, is the line that we've created. So this is kind of like the boundary of this constraint for the, we know there's going to be two roots, so like you could mirror this shape down here. But any root that lies on this line, it's going to have a settling time equal to, I mean a rise time equal to that constraint that we made. So we said it was 1 second. This is going to be the line of roots that have a rise time of 1 second. All right. But if we want the rise time to be less than that, because we're making regions for everything that satisfies the inequality constraint, what did we say? Let's go back here. Mine says we didn't define TR naught. Where did you define it? I put it right up here with the rest of our constraints. And I just said 1 second for now. So, okay, I want to... Now, when I fill the shape, I'm going to use these less than or greater than to help us decide what that shape should be. And I think this angle is the most helpful. This is saying the angle needs to be greater than. So if we go back here, where's my shape? We're going to want our angle to be greater than the angle on this line. So we're going to be filling in the shape like on this side of the line up here. So I want to color in this stuff up here, and we're just going to go up to pi, and then I'm going to mirror that shape over here. Okay, so I see that we have like 5 minutes left, technically. But because we're so close, we're almost there. I'm going to go maybe 5 or 10 minutes over just so we can finish this and move on to something else. Plus, you're going to love the figure that this thing makes. Trust me, you want to stay. You want to see it. Okay, so this is going to take some strategy, okay? And this comes back to how the fill function works. And you might already have some ideas of how we're going to fill this shape in. Let's talk about it. Okay, so we have our complex plane. We have like the stability boundary, which is a circle. And then this is the line that we just drew. Something like this. And the meaning of this line is roots on this line satisfy an equality, not an inequality. So the equality is that the rise time is going to be equal to, so this is the roots that are going to have exactly a rise time of 1 second. And then how about we mirror this? Because any root that falls on this line, it's going to have its friend. Just like Bob Ross says, every tree should have a friend, or everybody should have a friend. Same thing for complex conjugate. For complex conjugate roots, every complex conjugate root has a friend. So there's going to be a corresponding line over here. And then we know that to have a rise time less than that, the angle has to be greater. So we have to like be over here. And so what I want to do is I want to shade in this shape. That's the shape that I want. Now the way that we have to do this, we have to make this sequence of points that makes this like Pac-Man shape. So I have to go all the way over here, then I have to go around here, and then I have to go down here, and then I have to come back. And you guessed it, we're going to have to use like some flip up down. Graph looks kind of sus. It is sus. Yeah, this is Pac-Woman. Pretty sus, right? So we're gonna make this sequence of points. All right, let's do it. It's time to do it. It's time to do the work. Okay. Okay. How are we gonna do it? We cannot escape. No, you're not escaping this. You're in too deep at this point. Okay, you're in too deep. Okay. What I want to do. Real part. Let's do this first. Let's look at the first entry of that real vector. And you see that it's at 0.95. So the first entry of the imaginary is 0.93. So what that means is the first entry of that vector is actually over here, like right on the lip of the Pac-Man mouth. But in the strategy that I told you, I actually want my first point to be over here, like at the edge of the mouth. And I want to go this way. So the first thing I'm going to do, because I want to go in the reverse direction, I'm going to call this real TR2, because we're just calling everything 2. I'm going to flip that thing. I'm not satisfied. I want to go the other direction. Okay, so that's my first step. And then I'm going to do something more. Okay, so what I've done is I've built the sequence that starts at the edge of the mouth and goes to the lip. The next thing I want to build is the outer edge of this circle that goes just to here, to pi. So I want to go from here to here. So the way that I'm going to do this, I mean, it's kind of like building a circle. I mean, it is, but it's building just a part of a circle. So like instead of going from 0 to pi with a circle with radius 1, I want to start at this angle and then go to pi. Okay. So let's find what angle that is over there. Let's go to MATLAB again. This is the variable, the vector where I stored the angles. So I kind of want to see, like, what's the first angle? What's the last one? 0.6. This is the angle that I want to start with, and then build around the circle. So I want to go from this angle all the way to pi. So what I'm going to do, I'm going to use like a similar formula like this, except the magnitude of this part should just be 1, because I'm building something that goes along the edge of the circle. So the magnitude's going to be 1, and then I'm going to have cosine of the angles that go from the starting angle that I want. So the starting angle I wanted was like the first element of that vector. And then maybe I'll go in 0.1 radian increments all the way to pi. Oh wait, I think I need to do, wait, how many parentheses do I need? I think I want to do this, because I want to make this into a column. I want to make sure it's a column. So what I did is I'm having cosine of this. So I built a column vector in there. I think the transpose is important. Okay, let's keep going, because we're going to do the same thing with the imaginary part. Imaginary 1 times sine. And now I'm going to do this plot, but I'm going to do the fill command. Now this is only going to fill the top half of the circle so far. We're going to do this step by step. 2. Let's make it red. Need to rename the imaginary vector. Oh, okay. Imaginary, thank you, Kate. Red. Wait, I have to steal the code from up here. How do I do this? Fill, blue. Okay, so I just want line style none. And then I want to make sure I have my alpha. And that's what I needed. Are you following? We're making shapes. All right, let's run this. Ah ha ha ha. Okay, so remember what we did? So far, we went from the edge of the mouth out to the lip of the Pac-Man, and then we went all the way around the edge of the circle, and then the fill command connects it back to the original point as well. So I've built around this half circle shape, and now we need to do what we did before to like create the mirror shape. So so I effectively have going from here, then I'm going to here. So the next thing I want to add is going from here to here, back to here. Oh, buddy. Okay, but what we're going to do the same thing that we did for this one. I'm going to do the same strategy because we're doing the same thing. So I'm actually going to copy this. But I'm going to rename this as the third iteration of us mashing things together. Okay. And so what I'm going to do is I'm going to take the real TR2, and then I'm going to take the flip up down of that. I'm going to take the imaginary TR2, and then I'm going to take the flip up down of the negative. And then we're going to redo this plot, but we're going to change it to 3. And then this is now we're in the home stretch. Because this is going to make our beautiful shape. Oh, ho, ho, ho. All right. Now the region where everything overlaps, which is this weird alien Pac-Man creature within the Pac-Man, that's the region that satisfies everything. All right, let me show you some, because we're gonna put all the nice finishing touches on this. Let's make a legend. So this is why we did the P1, P2, P whatever for all of our different plots, because once we go to the legend, this makes it easy to specify things. P2, P3, P4. And then you have to make these curly brackets, and you give names in the same order as the plots. So like P1 was our stability condition, or like the stability boundary. I'm going to go to the next line. To go to the next line, you can do ... Okay, let's add, so the second one was the settling time condition. So I'll do comma, ... The third one was overshoot condition. Wait, I'll just do MP. ... Last one, rise time condition. So that's all 4. How about we run this? Now we have this lovely legend, but I want to make it prettier, in my opinion at least. I want to make it look a little bit better. Like the first thing you can do, I think it looks better. Wait, why is this all the way over here? Let's bring it over to the edge. We can turn off the box, because the box around the legend takes up a lot of space, and it kind of tends to clip the figure. So if you evaluate this, now it just has that beautiful, it's just like outside. A little late, but when did we get rid of the overlapping circle in the middle? We did that kind of at the beginning. I think you're talking about the overshoot condition where it had like an extra curl in there. Was it Monday or today? We did it today. We did it today. Okay, there's one more feature that I want to add. And that is Z-grid. And so all you have to type is Z-grid. Let's run this again. I don't think I'll ever be able to come up with a code like this on my... You could. You certainly could. All right, this made it look a little bit busy. Oh, this screwed up our legend. So now our legend has this data thing in it. What you need to do, you need to run this Z-grid before you run the legend. Let's put it up here. But I know that this MATLAB has some new stuff, and that's why I wanted to do it with you, because this code is going to be super useful to have, but it's got some new commands in there. Your figure lost its shape? Okay, so what ZGrid did is it overlaid this plot with a certain grid. But I want to explain to you what these grid lines mean. You see some numbers on here. So like let me like zoom in here. This like 0.1, 0.2, this corresponds to the damping ratio. So this 0.1 line, it's roots that have a damping ratio of 0.1, 0.2, 0.3, 0.4. And notice the overshoot boundary is like parallel to these contours. And that makes sense because overshoot depends on the damping ratio. It's the damping ratio is the only thing that the overshoot depends on. So our overshoot condition will always follow the contour of these damping ratio lines. Okay, these other like vertical lines that have this 0.3 pi divided by t, 0.2, these are the natural frequency lines. So this line corresponds to roots that have a natural frequency equal to 0.3 pi divided by our sampling period. And notice these lines don't line up exactly with any of the shapes that we've already made. I think the closest thing that it might be related to is the rise time condition. Like you can see this contour of our Pac-Man mouth. It kind of goes along this way. Well, the natural frequency also goes around like this. In fact, some people like to approximate the rise time condition with these natural frequency lines. But you can see they're similar, but not that similar. So I think you can't really trust those natural frequency lines for the rise time condition. This reminds you of electromagnetism, the black magic chart. Yeah, I know. Do or do not. There is no try. That was my Yoda. Okay, so now this is fun because this code is totally modular. So what I want you to do, I want you to play around with this by going up to the top where we specified some of these conditions. And so let's make the overshoot, I don't know, 0.3. Let's make the rise time faster. Like I'll make it 0.5. Run this again. And you're going to see the shape update. So the mouth opened wider. And if you make the rise time even faster, let's make it like 0.2. It's going to open wider even more. Oops. So these restrictions we program into this. Yes. So the utility of this code, because like remember how this is how the digital control system design process goes. You begin with some system you want to control, sure. But then you have to define, how do I want to control it? Do I want it to be fast, slow, whatever? And those are going to be in the form of performance constraints. This code is going to say, okay, give me the performance constraints, and then I will tell you, so in this case, the region where there's overlap, if your discrete time system roots fall into this shape somewhere, they will satisfy all of the performance constraints you specified. Now, the next part is defining a control law so that the roots of your closed loop system go into this region. And that's what we're starting as early as next class, I think. I think what I'm planning for Friday is to do a little control system demo. Why do we have TR less than TR not? I thought we would want the actual rise time to be less than our constraint. We would want the rise time, actual rise time to be less than our constraint. I think we're doing the same thing. I think we're saying the same thing. I might have, with those TR not values, I might have confused some things. But yeah, TR not is like the value at the constraint boundary itself. That's, yeah, those not variables. How'd you get the data out of the legend? Well, what I did, so when you run the legend command, you can label specific data sets. Yeah, you have to move the Z-grid before you define the legend. And this is why I did the legend this way, because like if you just do legend by itself, it's going to throw all of the data in there. But when I introduce Z-grid, it introduces some additional data sets that draw these like little dotted contour lines. And so I wanted to not have that in the legend. What's the best way to reach out to you? I wrote an email about the graduate project last week. I think I know which email that is. Email is a great way to reach out to me. I try to respond within 1 or 2 days. Sometimes it might take me a couple more days. So I will get back to you on that graduate project email. I think I know what you're talking about. It was like some trapezoidal something. Sometimes I look at an email and I'm like, this is cool. I don't know exactly how to respond right now. And then I just don't respond. That's probably a bad habit. Instead, I should say, hey, I read this. I'll get back to you. But yeah, that's just me. That's just me. All right, guys. So now, hopefully, you have a code that makes this beautiful plot. We're going to be using this over and over and over again this semester. So it's important that you build a code like this. So come back to these videos. If you missed something, if you missed one of these days, start at the beginning. You should be able to catch up. I won't post this because you got to earn this code. You got to go through the steps. But you can come back to the video and you can rebuild this. This class is getting more interesting day by day. I'm so glad. Yeah, I have a conspiracy theory that that guy who stinks and that guy who doesn't stink are the same person? Good grief. That could be. Imagine they have Twitch open on the phone and the computer. I've never seen them both in the same room. I mean, wait, no, hold on. That guy who stinks was in the room when that guy who doesn't stink followed the channel. I think. That guy who does not... Wait, that guy who does not stink is here. Oh my goodness. Oh my goodness. Man, the mystery continues. Yeah, this channel, it's getting some deep lore. Our community has some mysteries. I don't know. This is like cracking the Enigma machine, I know. When is the fight? Is the class over? Yes. The class is concluded. We have completed the code. Now we're just contemplating the deeper mysteries of human existence. It's giving me an error on this line of code. The real, okay, cosine angle 1. I'm going to copy your code into my version of MATLAB. And I'm going to see if it gives me an error. Oh, you're getting one too. Okay. Wait, where does this code go? Wait, this is the same. So I just copied in this line, right? It's the same thing as what I have. Yeah, what error is it giving you? Why is the Z-grid in such a weird shape, like it's curved? Oh, did you make sure that you need to make sure that this is a column vector? Like, what I'm guessing is that yours is a row vector. Like, did you put an apostrophe up here? Mine looks like a Jesus fish, so I get to reply. No, I think if you make the rise time too fast, I think you can get a Jesus fish. Let me make it like really fast. 0.1, will that do it? Yeah, I think this is wrong. Wait, if I make it even faster, what is it gonna do? Yeah, this is... There's a minimum rise time that you can... Okay, you do have an apostrophe. Hey, see you, Belka. Exceeds the maximum possible variable size. Maximum possible variable size? Never have seen that before. I don't know. Yeah, sounds like you can't get the TR1 angle. Yeah, maybe do, maybe try size of angle TR. Like, what does that give you? $501. Oh, see, okay. Wait, do you have the same? I'm gonna copy your code in here too. Let's see if it's the same. Yeah, you have the same. You have the same thing. Wait, are your lines up here the same? I was missing the dot before the division sign in omega n TR. Oh yeah, you need, I'm guessing there might be, oh, okay, so H Swan asks again. Sorry, I saw your question earlier. So what does the Z-grid tell us? I'm confused. All right, so let's go over here. Actually, maybe I'll just make a new figure and I'll just type Z-grid. This is what Z-grid makes. And actually, let's make axis equal so it's a beautiful circle. think Cowardly Bean, I think you must be missing a dot. Okay, so Z-grid is showing two types of contours. The contours that say 0.1, 0.2, 0.3, this corresponds to lines of constant damping ratio in, okay, so like the 0.1 line. Any discrete time root that exists on that line corresponds to a system with a damping ratio of 0.1. Same with this 0.2 line, 0.3, and so on. So basically, like if you were to go to, and the way you can make these lines, so like we have this formula for the magnitude of a root. It's e to the minus damping ratio omega n times the sampling period. So if you plug in 0.1 for that damping ratio, let's see. Okay, and then we have the angle here. Okay, if you plug in 0.1 as well over there. And then for omega n, you would say like, because omega d, or this combination can only go from 0 to pi. So, okay, I'm going to set the damping ratio equal to 0.1. The angle can only go from 0 to pi, so that lets me solve for omega d. And then from omega d, I can solve for omega n. Oh no, did my tablet freeze? No. But anyways, you can plot the magnitude and angle of the roots that have this damping ratio of 0.1, and that's what that line gives you. And then you can do the same thing. So these vertical lines that are kind of curvy, those are the lines of constant natural frequency. So any root that exists on this line, well, this is a little hard to see, but this says 0.3 times pi times the sampling period. So any roots on this line have that specific natural frequency. So having this plot just is a quick way to tell you, okay, if I pick a root that exists right on this intersection, I know the natural frequency from this vertical line, and I know the damping ratio from this horizontal line, and that allows me to quickly relate the discrete time root to the continuous time root. But it's just some extra information that you can add to your plot. Okay, glad that helps you. Does anybody else have other questions or concerns? Did you figure it out, Cowardly Bean? I'm guessing it's something with the dot, the element-wise multiplication. You have not yet? You could throw it in the chat, just like you did for your other code. Why don't you throw in your, like if you throw in like these lines right here, we might be able to see. All right, let's take it. Let's throw let's throw Cowardly Beans code in here. So you went all the way. I'm just gonna put like in the top. I'm gonna separate it. So this, oh jeez. Good grief. You're such a cowardly bean. Okay, I probably don't need all of this. Let's see. Yeah. Yeah. Okay. MATLAB is like a cowardly bean currently. Yeah. Wait, is this gonna give me an error? Let's see if I get the same error. Line 61. NTR. MATLAB is never wrong. MATLAB is the way. This is the way. Okay, let's break this down. Let's debug. In line 54, the zeta tr is not in the square root. Oh my gosh. Oh my gosh, cowardly bean. Is this right now? What does my beta look like? Oh my gosh, cowardly bean. Now your code works. AH Palela has saved your life. Your life has been saved. Wow. Oh my gosh. Nicely done. Figuring it out. Okay, I'm gonna delete your code. All right. You're very welcome. All right, everybody. Have a lovely day. We're going to be back on Friday. We're going to continue our study of digital control systems. It's going to be fun. All right. Adios.